ahead and record this, and I'll try to post it. All right. So this is a similar situation. This problem is asking. It says an oddly shaped object is weighed in air and it weighs 40 newtons. Then it's weighed while submerged in water, and we'll talk about what that means in a second. It weighs 30 newtons. What's the density of the material? And so it's sort of a similar problem to the one we just did, but instead for objects that are more dense than water, you can't do a fraction submerged thing for objects that sink. So here's the idea, right? And so I can say, look, the weight of the object in this case is equal to 40 newtons, right? So here's my object. And then what I'm going to do is I'm going to submerge it in water. So, imagine this is like a little scale, a little spring scale or something like that, right? And it's tied to my object. Here's my object. Right. And so now I have, I'm weighing it underwater. But if you look at the forces that are acting on the object here, I have a force of gravity, and then I have a tension, but there's also now a buoyant force, right? And the buoyant force is equal to the force of gravity minus the tension. Because if I do the sum of the forces in the y direction, they're T plus FB minus mg equals 0, right? That's the sum of the forces in the y direction. There's a tension up and a buoyant force up and a force of gravity down. And so that says that my buoyant force is equal to the force of gravity, mg, minus the tension, right? That's what I get for that. And so we can look at if we talk about the specific gravity for this thing, right? What I'm after is the density of the material. And so this is the density of the object divided by the density of water. And so I know that the density of the object is equal to the specific gravity times the density of water. So if I calculate the specific gravity, I can calculate the density of the object. And so what that's equal to, I'm just going to do a little magic here. And I'm going to say, look, this is the density of the object over the density of water. And I'm going to multiply the top and the bottom by the volume of the object. I'm just multiplying by 1. But what I get on top is the mass of the object. Right. And this is the mass of the displaced water. Right? It's the density of water times the volume of the object. That's the mass of the water that's being displaced. I'm going to multiply this by G and this by G, right? And this gives me the weight of the object. And this gives me the weight of the displaced water. Right? The mass of the displaced water times G is just the weight of the displaced water. And so that says this thing, the specific gravity, is equal to the weight of the object, which, by the way, is the thing we know, right? Divided by, that's just the buoyant force. Which is just the weight of the object, mass of the object times G, minus the tension. But the tension is just whatever it weighs in water. And so this is equal to 40 newtons over 40 newtons minus 30 newtons. which is 4. And so the specific gravity is 4. Which is just the density of the object over the density of water. And so the density of the object is 4 times the density of water, which is 4 grams per centimeter cubed. So those are two sort of interesting ways to determine what materials are made of without knowing, by either weighing them in and out of water or by floating them in water. In the previous example. All right. The video you watched yesterday hopefully was on Bernoulli's principle and flow rates and stuff. And so that's what a few of these questions are on. All right. So most of you got this right. All of my pipe drawings look like something out of Dr. Seuss. Like that, right? So if there's fluid moving through this piping system, as I'm pushing it through here, you can think of this thing like a syringe, right? If I'm pushing a volume through this piping system, it has to go faster in the regions where it's narrower. Otherwise, you would get buildup in between. If these guys were moving at the same speed, then there would be more fluid moving past this point than past this point. So there would be fluid building up in between. And since fluids are largely incompressible, you can think of liquids as bags of water, right? Or sorry, bags of marbles. You can think of water as bags of marbles. The atoms are kind of already up against each other. They can slide around, but they're stuck up against each other and not really compressible. The speed has to be faster here. And so since it's wider at A, it has to be, the water at A is slower than it is at B. And so this is where A was. This is where B was. All right. Maybe 30 seconds, maybe another minute, maybe another minute. A few people have answered, quite a few. All right. So we've addressed the question of where it's faster, and now the question is how much faster. And so this is where we have to talk a little bit about what's actually happening here, right? So for if I just look at a little section of fluid here, let's suppose, you know, the fluid's just moving this way, and I can watch it go, right? If I can see the individual atoms, if it moves some distance like this, right, in time delta t, so this distance is delta x, right? And the time it takes to go, this is like t1, and this is t2. It's just moving like that, right? That means that if I look at this as a little disk, right, this disk has area A, then the volume, delta V, is just the area times delta X, right? That's how much volume is delta V. And when I push that far forward, when this goes from here to here, I have to get, this has, you know, if this edge was lined up with this one, so this was at T1, then at later T2, I have to have moved the same amount of volume from here to here that moves from here to here in the same amount of time, because I have to make room in here for all the stuff that moved this far, right? I'm pushing that much fluid in here. And so if if this is area, if I call this area 1, say, and delta x1, and this area 2 and delta x2 over the same time interval, then I can say, look, delta V1 is that, and delta V2 is area 2 times delta x2. But that has to be the same thing as delta V1. And so, so these two volumes have to be the same. And so I can write this way. I can say, look, so hang on a second. I just want to make sure I answer the right question. And so the flow through these two things has to be happening at the same rate. And so I can say, look, the flow rate is just the change in volume over the change in time. And so that's equal to delta V1 over delta T, or also equal to delta V2 over delta T. Right, I should be writing in black. Right. This is just the flow of the volume per time through a piping system, right? It's not the speed, it's the volume per time. This pipe delivers whatever, a gallon a minute, or 30 gallons a minute, or 10 gallons a second, whatever it is, right? And it has to be constant through the fluid, because I constantly have to make, if this fluid moves, that fluid has to move by the same volume. And so that means delta V1 over delta T, as we said, is equal to delta V2 over delta T. And that means that the area 1 times delta X1 over delta T is area 2 times delta X2 over delta T. But delta X1 over delta T is just the speed of the fluid in here. Right? Delta X over delta X1, I should call it that, over delta T is just the how far the fluid advances in time delta T, right? And that's just the speed. And so that's it's just the area times the velocity is the flow rate. Which is constant. It's constant throughout the fluid. The volume per time that's going through any part of the fluid has to be the same. Otherwise, there'd be some kind of crazy buildup somewhere. As long as the pipes are full, that's what happens. So then I can say, well, look, if this is area A and this is area B, right, then I want to know the speed at B relative to A, right? And so I can say area 2, velocity 2 is equal to area 1, velocity 1, or velocity 2 is equal to area 1 over area 2, velocity 1. And that means the speed of 2 is the ratio of area 1 over area 2 times the speed at 1, or the speed at B is area A over area B divided by the speed at A. And so this is equal to pi times the radius at A squared. How about if I do diameter? Hopefully you can still see this, right? The pi's and the 2's, which get squared, cancel. I get diameter at A over diameter at B squared times velocity at A. Diameter at A over diameter at B is 3. I probably should have used A's and B's instead of 1's and 2's, but hopefully you get that. Because there's the area goes as a square of the diameter, the speed goes as the ratio of the square of those. And so if the diameter is 3 times as big as diameter at B, then the speed at B is 9 times what it is today. And so the answer to that was B. think most of you understood that anyway. Try that one. All right, maybe 30 seconds. Okay. So on this one, I would have you guys talk to each other. You guys have been doing pretty well on them so far. But I suppose I could leave a lot of this stuff. Let me just erase some of this stuff. So this is the flow rate. The definition of the flow rate is the volume per time. And a real source of confusion is people confuse the flow rate with the speed. And the flow rate in a piping system is constant everywhere. And it's because, at least for liquids, and most gases too, because they're basically incompressible. That's what I was saying earlier. Even with gases, you only really get compressibility in air when you have very, fairly large velocities, like a few hundred miles an hour through your pipes, and then you get compressibility issues. But for liquids, there's almost no compressibility, and we certainly treat them as largely incompressible. And that means that if I push a certain amount of volume a certain distance, like in this case delta x, I push this volume delta x, I have to make room ahead for that entire volume. And that means if I have a narrowing region, the stuff has to move faster, because if I move an amount delta v in a time delta t, this guy I have to move the same volume in the same amount of time. And so that means this region has to move, the speed has to move faster, so the flow rate can be constant. The flow rate, right? And the flow rate is the volume per time, not the distance per time. The speed is very different, right? But the volume per time is the same. I have high speed where I have a narrow area, and I have a slow speed where I have a big area, so that the product, the speed times the area, can be constant. And that's what we're making constant. And this actually is true even in things like traffic flow, where you have a bottleneck. The speed is faster in the area where you strip down to one lane, because the number of cars that have to go by any point per second has to be the same. And so if I have 3 lanes open here, right, and 1 lane open here, the speed's going to be 3 times faster on average in here. I know cars start, stop, and so on. On average in here, it's got to be 3 times faster, because there have to be 3 times as many cars going past per point here as 1 lane here, because you've got 3 lanes feeding into it. And it's the same thing with atoms. So the answer is E. The flow rate at the point A is the same as the flow rate at point B. The speeds aren't the same, but the flow rates are the same. Normally we write it this way, right? The flow rate, I think it has a little script F or something, is the volume per time. And that's equal to the area times the velocity, which is what was in the equations we wrote earlier. Have another minute. So this is Bernoulli's principle. This is another one of those cases where he suggested this in words, kind of the way I'm asking this question here. A guy named Euler, E-U-L-E-R. Gerhard or something, did a lot of math and physics. I think he was French, but I'm not positive. He's probably German. Anyway, Bernoulli's principle says this. This is Bernoulli's principle, right? Pressure plus 1/2 rho v squared plus rho gh is a constant. And if you remember way back last semester, we said the work done is equal to the change in kinetic energy plus the change in potential energy. And if you watch the video, this is sort of the way I derive this. The pressure is really the force, the thing that's doing the work. The pressure is pushing things along, and it causes changes in kinetic energy and changes in potential energy. But with fluids, we don't have masses, really. We've just got a constantly moving fluid. That's why we have these discussions like we were talking about flow rate a minute ago, because there's not a particular mass, there's just stuff that's moving. And so you have to come up with more appropriate physical quantities like density and things like that, rather than a particular mass. And so in that derivation, it basically shows that the pressure plus 1/2 rho v squared, so this corresponds to the work, this corresponds to the kinetic energy, and this corresponds to the potential energy, like that. It's a constant in the fluid. And so in places where the pressure is high, 1 or 2 of these guys are both is low. And the places where the pressure is low, 1 or 2 of these guys is high. As you move through the fluids, you can get regions where all of these 2 guys are 0 and this is big, or these 2 guys are 0, this is big, and so on. And so in an airplane wing, in regions where the speed is low, the pressure is high. If you look at an airplane wing, just sort of a classic airplane wing, really not modern ones so much, is that's not a very good one. Let me just try again. They're usually flat on the bottom, and they look like that on the top, something like that. And so the idea behind an airplane wing is that there's flow over the wing and there's flow under the wing. And because air has a certain amount of inertia to it, the wing is splitting these air molecules up, and some are going over and some are going under. And in order for them to sort of get back to the same spot, these guys have a longer path to go as the wing moves through. And so above the wing is low pressure, or I should say it, let me get back to that, is a high speed. And low speed. And so above the wing, I get a high velocity, and below the wing, I get a lower velocity. And so that means that one or the other of these guys is compensating for that. In the region where this is high, the velocity is high, this or this has to be low. Well, we've already said that in a gas, this doesn't matter very much. We don't do rho gh in a gas, mostly just in a liquid. And so for our case, we can just say, you know what? The wing is pretty thin. The pressure difference due to a meter in gas doesn't make much difference. And so it's this guy. And so in regions where this guy is high, this guy is low, and regions where this guy is low, this guy is high in the same fluid. And so if I have low speed, I have high pressure. And if I have high speed, I have low pressure. This provides some of the lift that airplanes get, not all of it, just some of it. And nowadays, lots of airplane wings will actually have what we call a symmetric profile. They'll be curved on the top and the bottom, because for a variety of reasons. Fighter jets do that, so they'll have the same flight characteristics right side up as upside down. So the pilot doesn't have to get used to a different sort of flying aerodynamics when the plane is inverted. And so mostly, and this is true with jet engines as well, they don't fly upside down, obviously, but mostly these airplanes get their lift from their motors and their jets, not from the Bernoulli principle. But like crop dusters and stuff like that, those guys will have this type of shape of wing, and it gives you a good glide. If your engines die, you can glide a lot farther on them because they're because you're getting additional lift from this effect. I appreciate your patience today, guys, and thank you for showing up, those of you who did. Hopefully we'll have class on Friday. We've got another chapter to do. We're going to do a chapter on heat, and then we'll have a test. So the test probably won't be next week, and it might be late the week after, but probably the week after, maybe the Monday after that. All right. Any questions, hang around and ask me. Otherwise, thank you for showing up, and I'll see you Friday.